Hello and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm Cliff Young. I'm a software engineer on the Google Brain team, where I work on co-design for deep learning accelerators. I'm one of the designers of Google's tensor processing unit, which is used in a bunch of Google production applications, including search, maps, photos, translate, and powered AlphaGo's historic 4-1 victory over Go champion Lee Sedol. I'm also an ACM member. To learn more about my background, check on the bio widget on your screen. For those of you who may be unfamiliar with ACM or what it has to offer, here's more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides timely computing and information published by ACM, including CACM, Communications of the ACM, and Q magazines. Access to the ACM Digital Library, the world's most comprehensive database of computing literature, international conferences that draw leading experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the updated ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you'll find some additional widgets and resources. If you're experiencing problems on the slides or audio, press the F5 key in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device, or you can close and relaunch the presentation. Control volume, adjust the master volume on your computer. If you have questions during the talk, please type them into the Q&A box at any time and click the Submit button. I'll organize the question as Dave speaks, and he'll reserve time at the end of the presentation to address them. The session is being recorded and will be archived. You will receive an automatic email notification when it becomes available, and check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out to help us improve our tech talks. You may also open the link to the survey at any time from the resources window on your screen. You can use the Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag #SharpACMLearning. We'll be watching for your tweets. We also have a new community discourse page to continue the discussion after this webcast, including questions we won't be able to get through during the Q&A session. Today's presentation is A New Golden Age for Computer Architecture by Dave Patterson. David Patterson is a Berkeley Computer Science Professor Emeritus, a Google Distinguished Engineer, and the RISC-V Foundation Vice Chair. He received his BA, MS, and PhD degrees from UCLA. Dave's Reduced Instruction Set Computer, RISC, Redundant Array of Inexpensive Disks, RAID, and Network of Workstation projects helped lead to multi-billion-dollar industries. This work led to 40 awards for research, teaching, and service, plus many papers in 7 books, including Computer Architecture, a Quantitative Approach, and his newest is the RISC-V Reader, an Open Architecture Atlas. In 2018, he and John Hennessy shared the ACM AM Turing Award. A former ACM president, Dave has also been recognized as an ACM fellow and has been honored with ACM's Eckert Mockley Award, Distinguished Service Award, and Carl D. Karlstrom Outstanding Educator Award. He's also a member of ACM. Dave?
Okay, no, I've dropped out of ACM. All right, well, I'm going to give a talk that's based on the Turing Award. If you want to see John Hennessy, my co-winner, you could click on that link in the talk I gave about a year ago. But in the first 15 minutes, I'm going to do 50 years of computer architecture. And what we're going to see is that there's 3 themes through this 50 years, is that software advances can inspire architecture innovations, and raising the hardware-software stack creates opportunities for architecture education. But kind of interestingly, in this field, it's the marketplace that ultimately settles these architecture bags. It's not a perfect arbiter, but that's how it works. Okay, so let's go back to the early 1960s. IBM had this problem. They had 4 incompatible lines of computers. Each had its own instruction set, its own I/O system, its own software stack, and it had different market niches as well. So IBM engineers decided they were going to try and fix this problem by having a single instruction set to rule them all, called the IBM System 360. Now, computer design then and now, the hard part is the control, the brain of the computer, not the brawn, not the arithmetic units. Those are pretty straightforward design. So that was the biggest problem for the IBM 360 designers. How could they get control correct? How were they going to convince all these kind of independent companies inside of IBM to work together and do the same thing with very different targets? Well, Maurice Wilkes, the second person to win the Turing Award, understood the difficulty of control, and he invented an idea to simplify control. He said, basically, since logic was expensive in his technology versus read-only memory or alterable memory, and read-only memory is cheaper and faster than RAM, let's specify control as a matrix, and we can think of those zeros and ones as programming, and he coined the term microprogramming. IBM liked this idea and decided to bet the company that microprogramming would let them to have a single instruction set across all these classes of computers. So in April of 1964, IBM made the biggest announcement in the history of the company, and here's an example of 4 of the models that they implemented. And you can see the data path width, the arithmetic units varied from 8 to 64 bits. The clock rates varied by almost a factor of 4. And then here's the prices in 1964 updated to recently. And, you know, that costs between $1.5 million and $9 million in today's dollars. So IBM bet the company, and they won that bet. And the person who led that effort was Fred Brooks, Jr., also a winner of the Turing Award. And so IBM dominated the mainframe industry for the next many years. Next up in our computer history is the mini computers that were built from integrated circuits. Logic, RAM, and ROM are now implemented using the same transistors, and semiconductor RAM is about the same speed as ROM. With good old Moore's law in full effect, over time the memory for control store could grow, and since it was RAM, not read-only memory, it was easier to fix bugs, so you could have much more complicated instruction sets. This whole called complex instruction set computer. And a classic example of that is the digital equipment VAX computer that had much more microcode than in the IBM 360 family instruction set. Now we go to the West Coast and come to the microprocessor revolution. Moore's law was going on, and microprocessors were getting more powerful, and basically they weren't computer architects, so they imitated the instruction sets ideas they saw in the mini computers and the mainframe computers. Typically, the way they would brag about their instruction sets, because people are programming in assembly language, they'd show example instructions that could use those new instructions, which, given that you had this microcoded interpreter underneath it, it was pretty easy to add instructions. Gordon Moore, to his credit, is certainly a visionary, and in the mid-'70s, he realized that the next instruction set they did after their 8-bit 8080 microprocessor was going to probably last the life of the company. So he hired a bunch of PhDs in computer science, sent them up to Oregon to invent the next great instruction set that was going to drive the company. It was eventually called the IPX 432, and it was certainly the most ambitious microprocessor project of the 1970s. So what they decided to do starting in 1975 was a 32-bit with address computer, going from 8-bit computers to have capabilities built into the addresses. It was a so-called object-oriented architecture, and they even wrote their own new operating system written in the language Ada. Alas, it had severe performance complexity problems and usability problems. So they had to go back to Gordon Moore, who told them to invent the next great instruction set and said they weren't going to be ready in time. He needed something in about 1978. It was going to take them several more years. So Intel was forced to have an emergency fill-in, which eventually was called the 886. This team was given 52 weeks to design a new instruction set architecture, the software stack, and build a microprocessor and make it available to hit that window that Gordon Moore needed. So the instruction set, only 3 weeks was spent on the instruction sets with 10 person weeks altogether. So not much effort. It was assembly language compatible with the old 8080, and they made some extensions to it. To their great fortune, IBM in 1981 needed a microprocessor, and they picked an 8-bit version of the 8086, 8-bit bus version of the 86. They really liked the Motorola 68000. Its instruction set was much like the 360, but it was late. So they went with the 8088. Now, that wasn't that big a deal from Intel's perspective because the 5-year projection of sales was just 250,000, 50,000 a year, not that big a deal. But they were wrong. It was instead they sold 100 million over the next 5 years. So the 886 became hugely valuable because all PC software ran on that instruction set architecture. So it suddenly had this very bright future. And Gordon Moore is right. It became the instruction set for Intel for the rest of the company. Now let's start taking a look at these machines of the 1980s. This is a picture of John Koch of IBM, a tremendous researcher and another winner of the Turing Award. Now you remember we talked about as a lesson that when you raise the hardware-software interface, that allows innovation. And what was happening about then is we were switching from programming in assembly language to primarily or exclusively programming in high-level languages. An example of that was, the Unix operating system was written in C instead of an assembly language. So now the output of the compilers is the source of the measurements. So John Koch not only did compiler work, he also built mini computers. And they decided to port their compiler to this IBM instruction set that we talked about earlier, but they'd only use the simple instructions similar to this mini computer made. Shockingly, using a subset let some programs run up to 3 times faster than using the older compilers by subsetting the instruction set to simple ones that ran faster. Researchers at Digital Equipment, where the VAX was made, measured the VAX and found, first of all, surprisingly, it took a lot of clock cycles to execute the average instruction, 10. They had expected it would be maybe 5. And when they looked at the microcode, they found that about 20% of this complicated instruction set was most of the microcode, but almost never executed. So that called into question just how valuable are these complex microcoded instruction sets. So this brings in the reduced instruction set computer. So what are the ideas? So the RAM that had been used for these microcoded interpreters was instead repurposed to be an instruction cache for user-reversible instructions. So it's more like compiling versus interpreting. And what this meant was the content of that memory could change depending what the program was running rather than just running an interpreter for an instruction set. The instructions are then pretty simple, just about as simple as microcode, just not as wide as microinstructions. And this turns out the simpler instructions enable pipeline execution. Microcode is often pipelined as well. And by the way, what are you giving up? Well, those complicated instructions of the RISC architecture weren't used that frequency anyway, so we're giving them up. And then there was a breakthrough by a person at IBM of a compiler improvement made it much easier to use registers efficiently, which benefited these simple load store architectures. So this is when the academics entered in Berkeley and Stanford. So this is a picture on the left of RISC-1, I think what's considered the first RISC microprocessor. We did this in a series of courses at Berkeley, and this is a group picture of the people who worked on it. A couple of these students decided to do a follow-on project to do a much more efficient one, which is sensibly enough called RISC-2. It came out a year later, and this is about the time John Hennessy got involved in about 1981, and his MIPS processor came out about the same time. The MIPS microprocessor at Stanford led to the company with the same name. Now, let me go back for a second. And oops. All right, we'll get there. Well, I can say what happened. I just remember when these projects were happening, it was presented at the Leading Circuits Conference, and it was a remarkable moment in time. There was a Berkeley and a Stanford presentation, is that these chips, RISC-2 and the Stanford MIPS processor, were plausibly better than any microprocessor that industry could make because it had a different set of ideas, and that seemed like a stunning moment. Now, part of the difficulty was trying to explain how this could be true. How could simpler instructions be better than complex ones? You'd need a lot more simpler ones. And we eventually came up with an explanation that this this formula shows. That basically the time per program is the number of instructions you execute. You have to execute more of the simple instructions. But the average number of clock cycles could be less. And it turned out to be about a factor of 5 less for the simpler instructions. So the overall was roughly, the RISC was about 4 times faster than the RISC architectures, as that slide shows. Now, that formula in the book that Henningsen and I subsequently wrote, this slide is kind of why we got the Turing Award, is the working of the RISC architectures, and then the book itself that helped explain how to design computers in general, and then the formulas like the ones which had never appeared in textbooks before this one, and we gave it this more quantitative approach. Okay, so what happened? So this is the PC era. So Intel, to its credit, figured out how to put 500 engineers to build a single microprocessor, which is quite an engineering feat. And they translated the x86 instructions, these complicated ones, into these simple RISC-like instructions internally. They would do that in hardware, kind of remarkably. And then any good RISC ideas could get used inside the x86. And that had this giant market because it was binary compatibility with software. It eventually got up to 350 million microprocessors per year at its peak. So the x86 instructions had dominated servers as well as desktops. So it basically, the marketplace picked it in the PC era. But it's called the PC era for a reason. Now we're in the post-PC era where the client and cloud. Now, instead of buying a microprocessor from a company, you're getting intellectual property that you're installing into a system on a chip, and that's a different case. And because the mobile version of this values is cost-sensitive and energy-sensitive, the extra overhead of the x86 architecture is expensive in both of those, and so less attractive. So now in the post-PC era, it's shifted to 20 billion per year and increasing of number of 32-bit and 64-bit microprocessors, and 99% of those are RISC. So in the marketplace, again, settled the debate, but certainly in the post-PC era, RISC has won. Okay, so that was pretty quick history of how things are going. Now let's talk about the current state of affairs. Shockingly, Moore's law is no more. This is a presentation of Intel points, dotting points about how fast Moore's law should be, and as opposed to the red line is where Intel actually is, and the blue line was Moore's law, and we're off by a factor of 15 in the number of transistors. Equally important, but less better known, is what's called Dennard scaling. And he made this observation that how can we keep putting more transistors in? Won't the chips burn up? And he said we would lower the threshold voltage so that the power per millimeter of semiconductor would stay about the same. And you see from 2000 to 2006, that blue line was pretty flat. But then as the technology continued to shrink, it no longer held Moore's law. The Dennard scaling ended, and we started using more power per millimeter squared. So power became the overriding issue. So the combination of those two things basically is the single thread performance of general purpose microprocessors is improving very slowly. In the RISC era, things were doubling every year and a half. Amazingly enough, for those of you who weren't there then, people would get rid of their perfectly good working computer because their friend's computer, which was a year or two newer, would be much faster, and you'd be jealous that you can't get your work done as fast. So you would throw a good laptop away, or not a laptop, a desk side computer away and buy a new one. These days, we don't do anything like that at all. But the end of Dennard scaling, almost eliminating the benefits of multi-core, has left this. So single thread performance is pretty flat going forward. So no Moore's law, no Dennard scaling, processor performance improving. There's more bad news. We've got this new kind of security challenges that are actually the fault of the microarchitecture of the computer, not a software bug, but microarchitecture. Spectre pointed out that you can do timing level attacks to see how things are used inside the computer to figure out information. And that seemed like a theoretical concern, but actually it's tens of kilobits per second can be leaked. So this is a big challenge for computer architecture, and we need new solutions to try and how do we prevent timing from leaking information. And so can hardware is kind of making it worse. Can hardware actually hide these problems or even make it better? So that's kind of a startling state for computer architecture to be in. What can we do about that? And there's an I like inspirational quotes. Our textbook is filled with inspirational quotes. But John Gardner, who was a Republican in the Johnson administration, who brought about Medicare, said, what we have before us are some breathtaking opportunities disguised as insoluble problems, kind of the definition of optimism. All right, so how are we going to make progress? Well, the first part is going to talk about performance, and we can be more software-centric, and that people are shifting away from languages like C to language like Python that are highly interpreted and very helpful for programmers' efficiency, but not so much for execution. And then also, in terms of the hardware side, the only path left that most architects think of are domain-specific architectures. They can't do everything like general-purpose microprocessors do, but what they do really well. And so the hope is that we can find domains that are important commercially that we can accelerate dramatically. And you can do both of those things, right? Improve the software and improve the hardware. And this is, again, one of these themes is that we're raising the level of hardware-software interface. Coincidentally, there are domain-specific languages, not because of the architecture problems, just because people wanted to program more efficiently, like TensorFlow or Halide. Let's make those programming of those applications go faster. That helps when you do special purpose architectures. So how slow is Python? Well, this chart shows this from, it's based on a paper for our colleagues at MIT. Let's do matrix multiply in Python. And first of all, and this is on a logarithmic scale, right? Rewriting it from Python into C, just that rewriting makes it go almost 50 times faster. Then we're running on a multi-core computer, in this case, 18-core computer. If we explicitly parallelize it with basically hints and things like that, we can't do this automatically in compiler, but if we do it explicitly, we can get another factor of 7 in performance improvement. Now, caches play this really important role. So can we take advantage of putting things optimally in memory to get the best use of the caches? And we get another factor of 20 from that. And then finally, the x86 architecture has basically SIMD or vector instructions that we haven't taken advantage of. They could do 16 operations per clock cycle if you can use those instructions, which you can for matrix multiply. And it's another factor of 9. So you put those all together, that's a factor of 63,000. So vastly, you can't imagine doing that in hardware. And as John Hennessey's compiler expert said, you're a hero if you came out with a new C compiler that would get you a factor of 2 on general purpose processors. So as John describes it, there's Turing Awards laying on the floor waiting to be picked up by people figuring out how to take Python and make it run a lot faster. So we're identifying opportunities for you to work on. In terms of, that's the software side. What about the hardware side, the domain-specific tasks? And basically, I think I said this before, it's not just for a single application. That's the only point. We didn't say application-specific architecture, domain. So we're talking about domains like video or machine learning or things like that. And it's not strictly, it doesn't just do one thing, but it does that domain well. So why? Part of the textbook is trying to demystify computer architecture. And basically, there's things that we understand that might not work well for general purpose microprocessors, but can work for these special purpose ones. First, are more effective parallelism for a specific domain. If you can use the SIMD style, that's more efficient than the MIMD style, like the general purpose microprocessor. Similarly, very long instruction word to get multiple instructions, operations at the same time is more efficient than the speculative out of order that's typical of the general purpose microprocessor. So the two on the right is what general purpose microprocessors do. Domain specific ones typically do the two on the left, VLIW and SIMD. More effective use with memory bandwidth. Well, caches were one of the great inventions, and caches are fantastic until they don't work. So they're probabilistic things that can work for many programs, but they don't work for others. If you actually know your memory access patterns, you can do that much more efficiently than a cache can do, and you'll see examples of that. And then unneeded accuracy. One of Berkeley's proud traditions is its participation in IEEE floating point standard. But you don't need 64-bit floating point numbers for some of these domains. In general, you want to have all the floating point formats, but for narrow domains, you can get away with smaller floating point numbers and smaller integers, and that makes things more efficient. And then the challenge has always been for special purpose architectures is where you're going to get software. Serendipitously, these domain-specific programming languages are writing things in higher levels, like in Python or in TensorFlow or PyTorch or languages like that in Halide, that raises that level of abstraction that makes it much easier to port that software to novel architectures. What are we going to accelerate? Well, there's a field where the number of papers per year is keeping up with Moore's law, and this is a plot that Jeff Dean did that shows the papers on archive, doubling every 2 years. So I think today, if you wanted to keep up with machine learning, you'd have to read 100 archive papers a day to keep up with all the excitement in this field. So that's a really good domain, and that's what Cliff worked on, and I worked on a paper on it, this TPU, what we call version 1. And this was written up in Communications at ACM in, I think, last September. So it's been in production use for 4 years. If you use Google, you're using TPUs, and it was mentioned it was used to help in that AlphaGo match to do that. So what's in the TPU? It's basically the heart of this TPU is astounding to me, 65,000 8-bit multiply accumulate units, 65,000 in one chip. You're used to having a few ALUs. The clock rate isn't very fast, but when you multiply 700 megahertz times 65,000 in this chip that's been deployed since 2015, it had 90 tera operations per second. And to put this perspective, a chip's time, that's 25 times as many multiply units as GPUs or 100 times as many as CPUs. Lots of memory on the chip for that dedicated uses, bigger than things. And it has some off-chip memory as well. The performance per watt of this chip, domain-specific architecture versus these more general-purpose things for the domain of machine learning is really impressive. It's the performance per watt is a factor of 80 better than CPUs and 30 better than GPUs. Now, when we wrote this paper, we used Google internal workloads, which was good because these are the things that Google cares about. These are important workloads, not just some toy program. But how can we advance this domain of machine learning? Because Google's not going to share its production workloads. So Cliff and I were involved in an effort called MLPerf that is trying to provide benchmarks for machine learning, much like the spec benchmarks did for CPUs. So it's public results were first last December. We had a second round that just came out this July. So I think it's been pretty well established. This was originally for what's called training, and they're about to do inference for MLPerf, which is what the TPU v1 was for. So we're standardizing the performance, and once we agree how to measure performance, we expect that'll lead to a lot of acceleration. For this training phase of it, what is demand? So this bottom part of the slide shows Moore's law, and our colleagues at OpenAI plotted since 2012 to 2019 how much have people been using, how much more people been using at the kind of bleeding edge. And that's that red line there. And this is a log scale, and it's much faster than Moore's law. Instead of Moore's law doubling every 18 months, this chart is doubling every 3.5 months. So that's more than a factor of 10 per year, which is astounding. So Google has gone on to build 2 more generations announced in the last 2 Mays of TPU v2 and TPU v3. TPU v2 is the one on the left. it can have up to 256 chips in a pod. It's basically a domain-specific supercomputer to do training. And its peak performance is a little over 11 petaflops. TPU-v3, which you can see the board that it's in, each of these have 4 chips, but the one on the left uses air cooling and the one on the right is a liquid cooling, it's liquid cooled, so it can be higher power and so higher clock rates. And we put more of them into a thing, and its peak is over 100 petaflops. So this is an attempt to try and keep up with that demand of OpenAI. You see, there's a factors of 10 between these two generations of the supercomputer to keep up with demand for training. And this is an example, that's the peak performance this is actually deliver. There's a paper that used a benchmark that's related to the one in MLPerf that shows these two generations of machines scaling pretty well up through 1,000 chips in the biggest design. So this is a very exciting time in computer architecture, and particularly about this domain, with lots of companies making different bets. Google, based on 1 or 2 cores, big cores per chip with these large multipliers with thousands of multipliers on it, and software-controlled memory instead of caches. NVIDIA GPU, which is kind of the one that most machine learning is done on, has 80 cores, and the latest one, many threads, requiring an amazing 20 megabytes of registers to keep all these threads alive. Smaller multipliers and cache, uses caches and has scatter, gather, and coalescing hardware, a very different architecture from the TPU. Microsoft has been betting on field programmable gate arrays. They put these in every server, and it allows you to customize the hardware. FPGAs aren't as efficient as custom chips, but they're much more flexible. Intel is kind of betting on everything. They have lots of core things, lots of caches, and making SIMD instructions that are going to match the domain of machine learning. They also bought Altera that supplies the FPGAs for Microsoft, and they also bought companies that do things like the custom chips like the TPU. And there's 100 startups out there, more than 100 startups. And I wanted to, how are we going to, people ask me who's going to win. I don't know. The architecture is going to settle this. But we just have to mention one of those startups that was announced last week at Hot Chips, which Cliff was on the session where it was developed. And this is Cerebus. Cerebus, right? Cerebus, yeah. So they're doing training, and what they call a chip is the biggest chip ever made. So the gray circle shows a standard so-called 12-inch wafer. As you can see, what they call a chip is just a full wafer where they just chop off the round pieces and as much as they can fit. That's 84 of these little rectangles, which, if you know, semiconductor is full reticle. So what an amazing thing. And what they talked about, not the performance, but just how do they cool it? How do they take advantage? How do they handle the expansion that happens? Just the physics of making that chip. And they'll later talk about its performance. But this is an example of the radical thinking that's going into this. We see people using analog computing and asynchronous design. All kinds of ideas are being resurfaced in this domain-specific architecture to see if that works well or not. So this is a very exciting time. Okay, so that was domain-specific architectures and software. What else is going on? And so for a long time, I was kind of jealous of my colleagues in compilers and operating systems because there were open source versions of them. They could either work on them in their research or in their classes or contribute code and make improvements that everybody in the world can use. Why not for instruction sets? The stuff that I work on. So this is where RISC-V comes to the story. So it's called RISC-V because there were 4 RISC projects that I led at Berkeley, and then this one that's happened in this last decade, they kind of honorarily named it RISC-V after that. That's why we use Roman numerals in RISC 1 and 2, so that's why it's a V here. So in 2010, it was time to do a research project, and we needed an instruction set. ARM and x86 made the most sense, but it was impossible to choose things. Those are really complicated architectures, so they're not great for research. And we weren't allowed to do it. We even were sponsored by Intel, and they didn't want us to use x86. They wanted to protect that stuff. So we started in May of 2010. We started a short project to develop an own clean state instruction set, learning from history, not to make the mistakes of the past. It was really, I provided the wisdom, but Krista
Asanovich, Andrew Waterman, Jensep Lee, the last two are grad students, now have their PhDs, led the design. 4 years later, this spec was frozen, but we built a lot of chips along the way, which is a good thing to do when you do instruction sets. But we had this funny thing happen, is we were using it in our research and in our courses, and we started getting complaints from industry of people saying, well, in the fall, you changed the version of the instruction set from the prior spring. Why did you make that change? Like, well, here's why we did it, but why do you care? This is for our internal use. And we found that there was this thirst for an open architecture, and people had cast around and found ours and found it as an attractive thing. Let's start using it. So once we heard about that idea, we thought that would be very cool to help make an open instruction set architecture that everybody could use for all classes of computers. So that's what RISC-V is. So what's different about it? It's free and open. So anyone can use it. And I think what this is going to mean, there's going to be more competition. So right now, we're kind of 3 or 4 years into this as an official open project. There's more companies building microprocessors around RISC-V, designing them from scratch than for any other architecture. Usually there's just one company that can do this, or maybe there's 10, but there's dozens who are doing this. So I think this is going to mean more innovation. For startup companies, what's attractive is normally you pick a proprietary instruction set, you have to sign a contract with the vendor. This time you can pick the open instruction set, and you later figure out who's going to do it. And there's even some ones that are free and open that you can use. There's open implementations of this open architecture. It's for both the cloud and the edge. We have 64-bit and 32-bit versions, and there's optimizations both for big computers and smaller computers, and that's just the right thing to do in the modern world. You can have an architecture span all those things. We know how to do that now. And then a big concern in this modern world is secure and trustworthy. The Snowden tapes showed that sometimes governments will sneak stuff into technology, and so people became worried about that. So many countries would like to make sure they know what's in their computing infrastructure, so they design their own cores. So by being open, you can design it yourself within your own country. And also these open implementations that you could download. By being open, it's less likely to be trapdoors because lots of people are looking at it. It's a really simple and elegant instruction set. Going back to the original RISC ideas, we wanted to keep it simple and elegant so it could track Moore's law. There's a lot of benefits to that. Far simpler than ARM and x86. I've come to learn over the next few years, there's basically a marketing reason to expand your instruction set. If you're selling IP or you're selling a computer, you have financial incentive to make it more complicated because you want to get more money for people or get people to upgrade. And it's harder to do that by saying, well, this is better and runs benchmarks a little better. It's a lot easier if you just say, look at these great new instructions that you can have. We're keeping it simple because there's no technical reason not to keep it simple. There's just marketing reasons to make it more complicated. And then given this world that we talked about, domain-specific, you have to have an architecture that you can add domain-specific instructions to, and that's kind of easy to do. If you know about this advanced, you just basically need opcode space for these, that people can use that. And then what's different about this open architecture we've come to learn about, typically what the problem is for an architect is you announce a new version of the instruction set architecture or some upgrades, and then all the software people tell you everything you did screwed up on, and then you do another iteration and another iteration. Because it's kind of like a standards effort, we get all these software experts in advance before we settle on it, and we have this debate before it's announced. So it's a little bit slower doing it that way, but we get it more accurate. And then finally, university research projects can lose interest in things that are commercially important. So like other open source efforts, we needed to have a foundation to drive it, not just leaving it up to Berkeley. So there is a RISC-V foundation, and it's been around a couple of years. It has almost, I think it has 300 members of various forms. So you can see there's one cluster around signature IP and design services, one around development tools, one around consulting, and one around machine learning, commercial chips and application focus. And this is another version of this chart showing it's up and to the right. This chart was May, so we now have more than 300 people. But you can, it's like 28 countries around the world are doing RISC work, and the number of organizations and people involved rapidly increasing. And open architectures aren't just limited to RISC-V. NVIDIA opened their implementation of their training chip as well. All right. So I think security community really likes open architectures. They like that and they like RISC-V because it's pretty simple, and open architecture and open implementations. This is all what they like. They don't like security through obscurity is not popular there. And because it's open, everybody can work on it. And security is so hard, we want all the best minds working on it. Plus, there's an implementation you can download, and with FPGAs, they can run pretty fast. Fast enough to run real software stacks, not as fast as hardware, but it's fast enough you could put it on the internet. So we can make security experimental rather than just, people arguing about it. So I believe RISC-V is already becoming kind of the primary vehicle for the security people. So let me wrap up. The final thing is that software can inspire advances is the agile development method, where you work in small teams and do short development cycles to get a prototype before you go on to the next step. We've been using that in designing hardware. So the so-called Scrum team organization keeps these teams small and do these small sprints before you iterate. And so the new CAD software is allowing us to do that, and we're doing what's called agile hardware development. So at Berkeley, how can you do that given hardware? But it's really many layers of the design. If it's a software simulator in C++, you can easily modify that. If you want to do more cycles, field programmable gate arrays is much faster than simulators, but that's clearly easily modifiable as well. Then there's even some on the web now. You don't even have to buy hardware to do that. To get an idea of area and energy, you're going to have to put it through the ASIC flows, but that's still layout. And then there's some manual work that has to do. Now, when you get to that point where it's ready to tape out, you still haven't spent any money. And that's a pretty good approximation of where you are. You could guess things, but the excitement of computer hardware is building chips, getting chips back. It's like Christmas, when they come back, do they work or not? How fast are they? How much power do they use? So it'd be, to me, stopping at being ready to tape out a chip is like preparing for a marathon and running up until 200 yards from the finish and stopping because you could guess your time, right? You missed that payoff. So tape it out if you're going to get ready to do. And you would think that'd be very expensive, but because there's something called test chips, you can do small chips that still have millions of transistors for only $14,000. And you would do, if you want to do a big chip, it's more expensive, but you can demonstrate a lot with small chips. So wrapping up before time for questions here. So that I said there's a theme that software advances can inspire architecture innovations. Microprogramming and RISC were examples in the past. We've got these new ideas of open architectures and agile hardware development. Raising that hardware-software interface enables architecture opportunities like RISC from high-level languages. And now for these domain-specific languages at higher levels are allowing domain-specific architectures. And the marketplace is going to settle this. When things lose, it's kind of a disaster, but things can last for decades if you succeed, like x86 and the 360, and now RISC in this post-PC era. The open versus proprietary and which thing's going to win machine learning is too soon to tell, but surely the marketplace is going to settle it. But this is a very exciting time to be a computer architect, which is why Hennessy and I titled our Turing Award lecture that way, and we're ready for questions. Oops. And that's a paper on it as well. All right, Cliff, you going to ask me questions or?
Yeah.
Okay.
A wonderful talk, and let's move on to Q&A.
You going to ask me questions or?
Yep. Thanks, Dave.
The first question I have up.
I've got a little bit of lag on my audio interface.
What are experiences with hardware and
The
software?
question I have up is, he asks, what are experiences during design of a new product? Are there problems?
What are the experiences when the? Yeah, well,
to me, this goes back to the RISC ideas. Is you needed to have compilers and the architecture together. It didn't really matter if you had a great hardware idea if the compiler couldn't generate code for it. So I think computer architecture has always been this collaboration. What's different now is it's really there's a lot more layers involved, all the way from the applications. Since it's domain specific, right? You have to know about the domain. There's not just some random C programs that you just have to accelerate. So it requires more cooperation across those layers, and it's very exciting to do that. I think Cliff and I are enjoying being at Google because in the area of machine learning, we're in this brain group where we have machine learning experts, and of course there's people here at all levels of the stack. So when you find a group that works together, it's really exciting because you feel like you're pushing forward this new frontier. In terms of the problems, you need to understand each other's jargon. Sometimes the jargon makes things difficult, and it takes some more time to teach each other what the issues are. So it's a little bit slower than if you just ignored all that stuff, but it's very satisfying when it works.
Sorry about the delays. A little bit of microphone bounce here because of echoes.
Okay.
A security-related question, which is, does RISC-V do anything to address the Spectre
Question, which is, does RISC-V do anything to address the Spectre and solely on the chip design?
RISC, because of the opportunities around security, we actually have the RISC-V Foundation has a standing committee on security. There's so much excitement. Right now, the RISC-V architectures don't have this problem because they're not as aggressive as the x86 architecture designs with the extreme out of order execution and things like that. There are papers being written about people coming up with ideas of how to hide that, make it difficult to do that information, and I think these papers are being using RISC-V. But so my hope is when somebody does build an aggressive out of order execution machine where there's lots of sharing going on, they'll incorporate those ideas. But so far, RISC-V doesn't have it, but that has to do partly because of the lack of very extreme implementations. But the good news is, it doesn't have a bunch of legacy interfaces that also cause some of the problems that people are attacking. So it's probably got a better shot than the older architectures.
Okay, I'm going to try just talking in the room and hoping that this question is heard through the mic that Dave is wearing.
Okay.
From Jan Timanowski, there's a question from the discourse forum, which is, what are your thoughts about how this will change computer science education? For example, will undergraduate students still need to learn about instructions and architectures in the assembly language? I can imagine the possibility that CS education will have two tracks, application and systems.
I think if you want programs to run fast, you should still understand computers at the instruction set level. I think if you don't give them a model of what's underlying your applications, they'll make up their own that could have nothing to do with how hardware really works. So I think you have to understand how hardware works if you care about performance. If you don't care about performance, then I think you could probably get away without worrying about it. For me, the educational excitement is we can actually have people, and if the path forward seems to domain-specific architectures, we could actually have students, because of RISC-V and because of field programmable arrays, students in classrooms could add their own instructions to a realistic computer and run real software on it, and they could see the acceleration that they do from it. So it's a particularly great time to be an educator with RISC-V and field programmable gate arrays for people who want to go into greater depth.
A question from Cyprian Cornilla asking, if you were a computer engineering student in 2019, which one of these areas would you pursue?
Which one? Well, I think computer architecture is a great opportunity. Most people are going to assume it's software. I can say that people who understand machine learning computer architecture, there's a great demand for them.
And these ideas would, I think, serve you well. But I would, you should probably think about the long-term career here, not just what's in the next couple of years. I think computer architecture, the ideas of machine learning are going to be pretty important for the next couple decades. So I'd try and learn both of those things if I were you.
And we have a request that you repeat the questions that I asked.
Okay.
Some of the time are they coming from
Okay, this was a question about what should I answered the question. If you were a student in 2019, what would you study?
From Anthony Gargaro, there's a question. In the 60s and 70s, CDC built some of the fastest computers using a reduced instruction set architecture. However, you didn't mention them. Is there a reason why you didn't call the CDCs a RISC architecture?
Well, if you actually go back and read, not that you might want to, but if you go back and read some of my early papers, the question was, weren't CDCs RISC architectures? And in the papers I said, Seymour Cray, one of the greatest computer designers of all time, designed both the CDC computers and the Cray 1 computers, and my papers say that is that those are pretty much RISC architectures for the time. They concentrated on floating point performance rather than the integer performance, and paid less attention to compilers at the time. That was less important to Seymour. But yeah, those are clearly examples of RISC architectures.
Next question from Vijay Ganagapati, Qualcomm. What percentage of machine learning workload, training and inference coming into Google servers is sent to TPU? I heard Google also deploys a lot of GPUs to address cases with new deep learning architectures that TPUs can't handle.
Great. So this is a question about TPUs and GPUs. Cliff's got, I'm this academic recently in industry, and I have to be careful what we say. TPUs are very heavily used inside of Google. I think but we also have GPUs. That's probably all I can say. But yes, I can tell you that people really here are excited about future generations of TPUs and what they're going to be able to do with these kind of supercomputers we're building.
Question from Steve Wilson of Phoenix Electronics. You didn't talk much about where general purpose processing goes. How successful will many core processors be, and what other options are there?
The question is, how come I didn't say much about general purpose processors and what's their future? It doesn't look good. I think it's possible to right now, if you could figure out a way to cool the chip better. So there's two issues: not having hotspots and just getting the heat out of the chip. Server chips will be able to use, if they use more power, they can put in more cores. But the cores themselves are not a lot faster, right? So it's hard to be optimistic about general purpose computing. I mean, because of software compatibility, people are going to keep buying them. But the future path to significant performance or energy improvements is domain-specific architectures, and that's where the excitement is. So I think the value proposition is going to be around the accelerators more than it is around the kind of classic instruction sets and software where it used to be. So that's a pretty big change in what's going on. So I find it much more exciting because you can get these giant speed ups, for these domain-specific architectures, factors of 10, which are amazing for commercial things. Where for general-purpose processors, you're talking a couple of percent improvements, and that's kind of boring thing to work on. So that's why I didn't talk about it much.
I think I'm going to fuse a couple of questions that came in. One was, do you see a role for application-specific processors in other areas, say databases or networks? And the other, this similarly themed question that came in is, can you give another example of where domain-specific architectures can be very useful, apart from ML domain? Yeah, apart from ML domain, I mean, a real obvious one would be video. Yeah, a huge fraction of what's going over the internet. I mean, I don't know about you guys, but I'm watching stuff where movies are, my entertainment's being downloaded over the internet every night, and so compressing video is hugely financially important. But besides applications that are kind of batch processing, I think the path forward is going to be accelerators. So I expect heterogeneous systems, maybe more tightly coupled than right now to what's being done for GPUs and TPUs for machine learning, video with separate memory systems, something that's more tightly coupled.
Databases would be an example of that. But I think we're going to see, over the next 5 years, much more heterogeneous designs with lots more accelerators. An example of that today, right now, is cell phones. A cell phone SoC has a general purpose microprocessors and maybe 15 or 20 other kind of accelerators. I think servers are going to look like that in the future, maybe even laptops.
Somewhat open-ended question. Is there a resource website where we can learn about these topics from basic to advanced levels?
A website. There's a textbook. There's got to be, This is my textbook. The 6th edition has a new chapter on domain-specific architectures and talks about machine learning in that. Do you know of a website, Cliff? I don't know if it's been collated into a website.
At the intersection of architecture and machine learning, I'm not aware of a single website that's great on it. There are some wonderful blogs about performance tuning for NVIDIA GPUs.
There's if you want to see performance improvements for NVIDIA GPUs, or even there's some on TPUs too. There's blogs that both companies have written that kind of explain what you do to do that. And probably GPUs are so popular, there's probably things besides NVIDIA's on that.
Next question, I'm going to broaden it a little bit. The original question was, what have you learned that software needs to focus on in an OS or DevOps level? But I think we should broaden that to, what do we have to worry about in software for these general accelerators?
Yeah, what's the software challenge for these accelerators? Well, it's going to make things. This is harder, right? That's why we have general purpose computing is a much better solution. It's much easier that you're writing, writing programs and the compiler's matching it to the hardware, and it's a simpler compiler job when there's a single instruction set you have to deal with. This is going to be harder for our software stack. I can imagine something like maybe like a function level interface or some kind of API interface where you're interacting with these accelerators. It's going to be a more difficult challenge. The good news is that if we're using domain-specific languages, they tend to be not a lot of number of lines of code. So if you're writing in TensorFlow or writing in PyTorch, the machine learning piece, that piece we can retarget. But you're going to be developing software that has, a C++ piece and a TensorFlow or PyTorch piece, and that you have to break your application up into those pieces. So this is going to be, it's going to demand more for programmers. One way to think about it is, if you want to be a ninja programmer, before you just had to kind of understand C++ and x86 architecture. Going forward, you're going to be a ninja programmer. You may have to know about GPUs and TPUs and many more domain-specific languages to be able to get the best performance out of your systems.
I think we only have time for a couple more questions. I'm going to move a little bit farther out in the question space. The next question is, what about quantum computing related architecture?
What about quantum computing? I think I don't know if I have a slide on it. Yep. Oh boy, that was really, the slides still come up. So I get this question a lot, so I decided to look and see what's done, and just wanted to say this is science, right? This is big science. This is not going to be for your cell phone. And a recent workshop said, there's been a lot of excitement around quantum computing, but the applications isn't clear what the next application in the next 10 years. And this was done by a computing group, but the National Academy of Engineering also wrote one that had similar conclusions. We got to be careful. This might be a 2030 kind of solution, so we're going to need something over the next decade until quantum computing works. So, it'll be great if it works. Like if nuclear fusion works, that will be great, but it may be a while before this happens.
And the last question we'll ask is, what are your thoughts on new devices such as memristors, spintronics, and integration with silicon-based activities?
These new technologies are exciting. And there's two things to say there. It doesn't look like there's anything that's going to be commercially viable within the next 5 years that's going to change things, or maybe it may be more like 10 years. Second thing is, over my career, there's been all kinds of promises of new technologies, and most of them don't work out. Partly there may just be a flaw in the technology, but also to work, they have to have a commercially viable way to increase volume. They won't go from zero to suddenly, billions of parts per year. There has to be where they're at the millions and 10 millions and so forth. And so they have to go into a product that can use them at their current state of technology. And that's been it's been this cliff that a lot of technologies have not been able, or this gap that they haven't been able to cross. So, I'm rooting for one of them that came along, but in the meantime, we're going to have to use existing semiconductor technology for at least the next 5 or 10 years. And we want to keep getting faster computers and more energy efficient computers. So hence, the topics of this talk, which is going to fall a lot on computer architects.
Put your microphone up.
Okay.
Sorry.
Oh, okay.
Oh, okay. So I'm afraid we're out of time for today, but I'd like to thank Dave again for his informative presentation and insightful answers to the many questions. Special thanks to taking the time to attend and participate today.
This talk was recorded and will be available online in a few days at learning.acm.org. You can find announcements on upcoming talks and other ACM activities at learning.acm.org and acm.org. Other speakers, which you should see on your screen. On behalf of ACM, Dave Patterson, myself, Young, and for joining. I hope you'll join us again in the future. Concludes the talk.